Good morning, everyone. Thank you for coming to our presentation. Today, we're going to be talking about time series clustering for stocks, a project that Team 4 has been working on for data mining class in summer of 2021. Our team members who are going to be presenting today are me, Jake Cooper, David Gilstad, and Brandon Morgan. We're excited to show you the results of what we've been working on. Just over the course of the day, real quick, we're going to talk through the introduction. I'll give a quick overview of the project and what it is, go into the related work and kind of the background, and then we're going to get into the meat of it with the proposed work, including the data set, algorithms, performance, system architecture. And we'll talk through all that stuff. And then finally, after the conclusions, we're going to give you a quick demo of the tool and how it actually works. So let's dig right in. So the essential idea behind this project is that in terms of stock market analysis, there's been a lot of focus over the past several years on using machine learning within the stock market and trying to make predictions for stocks. The reason why this is a hot topic button issue is just the fact that billions and millions of millions and maybe billions of dollars can be on the line for someone who successfully creates a model that can predict stock performance in the market. However, due to high market volatility and complex systems, this can be a very difficult task for supervised learning to actually accomplish, even for the most sophisticated neural networks we have around. So the idea behind this goal project is, what if we tried to make it simpler and use a combination of data science and more analytical techniques that are common within the industry. So the goal we have is to predict stock market trends through the use of conjugate stock analysis. The idea of a conjugate is a very common use by engineers and scientists in fields where you can't actually directly observe the system that you're working with. For example, geologists and petroleum engineers use this commonly. They look at how one well is performing in order to kind of predict how another well is going to perform, because they can't directly interact with the system that's at 10,000 feet underground. Similarly, how a single person can't really affect how the stock market trends. You can't test it. So you can use conjugates. So the goal really coming out of this will be to identify sets of quality conjugate stocks through the use of unsupervised data mining techniques. And the solution, how we're going to implement that, is an application that can build a cluster for any given stock based on the representative data set. An SME, a subject matter expert, can put in a stock that they want to analyze, and the tool will output a cluster for that stock, recommending conjugates to look at. Some related work that I'm going to talk through that's been kind of in the same realm of this, as I've been talking about, I mentioned before, in the stock market analysis world, a lot of work has been done with supervised learning, with neural networks. This is talked through a little more in our paper, but people like Yoshihara et al. And Madu et al. Did a lot of work to apply advanced neural network techniques to predict stock market, but ultimately, none of them have been perfect. All the error rates are continuing to be high until we advance this further. However, there are also, simultaneously to the advancements in neural networks, there have been a lot of advancement in time series clustering that we really think can empower this analysis and empower stock market predictions through the unsupervised learning in combination with our SMEs. Methods like k-means clustering have been improved for time series with the use of new distance measures like dynamic time warping, or DTW, which essentially measures how far away one sequence of time is from another sequence of time. And this can change in both the X and Y direction. So it can pick up if one sequence is just slightly off than the other. This is something that Euclidean distance would in the past not be as successful in measuring. Other newer clustering techniques like density peaks and hidden Markov models have also been successful and implemented within the realm of time series with certain modifications. Tadpole is a new common density peaks based algorithm that has been modified for the use of time series. And we'll get into a little more of the exact algorithms that we've used in a couple slides here. So once we kind of had the idea for the project and where we were going with it, the next step was gathering the data. Essentially, we compiled a data set with 400,000 rows of market data for 543 different stocks. We chose a couple different categories of stocks in order to try to make the data set representative. We chose the S&P 500 just because those are generally considered to be trusted stocks by the market, stocks that have a lot of history and are doing well. And then in order to facilitate some diversity in the data set, we also included the top cryptocurrencies performing and also some of the top commodities like natural gas, gold, and corn. Kind of add some variation and see how we expect those to trend with each other or with other markets. Next, after we gathered the data set, the next important step would be to do some data pre-processing that David's going to talk us through.
Yeah, so here we have a couple of things we did for the pre-processing. With our data, there was a couple of things to consider. First is that it's a time series, but also that it has high volatility. As you can see here on the left, we have the time rollup. This has a couple of purposes. So firstly, some of the stocks, namely the S&P 500, are only available for the weekdays, whereas things like cryptocurrency are through the whole week. For this reason, it's better for us to do a week rollup or greater, as it allows us to compare stocks with the same days. So another thing it allows is for the algorithms to process faster, as some of them can take hours and even longer for really short time rollups. Sorry, excuse me, really long ones like days and 5 days and weeks. So secondly, we also needed to normalize the data. And we chose two techniques for doing this. The first one was z-scores, which simply changes the values so they are all of similar, as some stocks can range from the price of 80 to sometimes being 500. The next one we used was a novel technique called adaptive normalization. And it accomplishes this goal of also normalizing to a specific set of values, but it also does two additional things. The first one is called moving averages. And what that allows us to do is to smooth out the stock and help get the trend and eliminate some of the noise and also some of the outliers that can be found throughout the stocks. The second part of the adaptive normalization is used as what's called a sliding window technique. And what this does is it allows us to get rid of some of the macro trends. So rather than picking stocks that have a couple of huge jumps, it's going to reduce those and normalize the data so that some of the smaller jumps, which still show the trend, end up in our clustering. And the third thing we do is the data imputation. And what that allows is, so some of the stocks on here do not have the same length of time on them. However, for comparing reasons, this is important that we are comparing over the same range of time. So what we did for this is we tested different types of backcasting, and that allowed us to essentially predict what they used to look like in the past. And that allowed us to compare from a larger range and therefore get better clustering. So now we move on to our algorithms that we will be using. And we really had two different types of algorithms. So the first were our k-means based algorithms and our density, and then our density peaks based algorithms. So for k-means, how these work is you first pick a set of clusters. Then you're going to assign all the data points to each of these clusters based on their distance from them. From then, what we do is we calculate averages and create new clusters, new sensors or centroids to use for the next iteration. From then on, we continue this process. We have two different algorithms we implemented for this. We have soft DTW. As you can see, it uses the soft DTW distance. And then we also had IK-means, which uses Euclidean distance. So soft DTW, as we said, uses DTW distance, but also as a way to perform a heuristic rather than directly calculating the next centroids based on the averages. IK-means, what it does is it uses Euclidean distance, but it also breaks up the data into ever increasing sizes in each iteration. So maybe it starts with 4 points, uses that to perform the k-means, and then maybe it moves on to 8 points and so on until it has the full data set. For next ones, we have density peaks. And density peaks uses a completely different approach from k-means. So rather than assigning clusters from the start, what it first does is calculates the distance between each point and every other point. Then using those and a minimum cutoff value, it decides which points or how many points are within that cutoff value to every other point. So from there, we can get the points with the highest density, or in other words, most points within a certain range. And we will use these points to build our clusters. So the clusters are built by taking all the points that are not the higher density points and assigning them to the closest higher density point. For these two algorithms, we used a straightforward density peaks where we used Euclidean distance. As Cenk mentioned, we also used tadpole, which uses DTW distance, but only when necessary. And when necessary is, so what it does is it looks at the lower bound and upper bound matrix, and if it can determine if the lower bound is above the minimum distance, then those 2 points aren't closely related. Or if the upper bound is below the minimum distance, then those 2 points must be close together. Otherwise, it has to calculate the DTW. Next, we'll move on to our performance evaluations. So as you can see here, we have the total sum squared errors for different rollups. So we had a yearly rollup where we used adaptive normalizations. We also have a 2-week rollup where we use adaptive normalizations. And we did a yearly rollup with z-score normalizations. So what can be seen from these slides, this slide, is that the TSS seems to be much higher in DP and tadpole. However, this actually makes perfect sense because the the k-means algorithms work by minimizing this TSS, whereas the DP algorithms do not do that at all. And what I mean by that is k-means, what it does is it looks for stocks that are close together, and it forms a somewhat circular cluster. However, for DP, it can form, and as it boasts, it can find arbitrary shapes in stocks, and which will inherently lead to higher TSS. When we actually examine the stocks and the clusters, we find that DP and tadpole did a pretty good job of clustering these. They just simply weren't, TSS just simply doesn't cover this very well. You can also see we have our runtimes pictured on the right. And while density peaks and IK-means performed very rapidly, since they used Euclidean distance, our soft DTW and tadpole, however, took a much longer time using dynamic time warping. Soft DTW, in fact, so much that we considered it to not be considered to be an ineffective for our tool. Tadpole performed a bit better, but also still took a very long time to run. And there are trade-offs to this. They may have done a bit better job clustering, but as you can see, they ran a lot longer. So next we move on to some more performance evaluations.
All right, so my name is Brandon, and I'm going to be covering the performance evaluation part 2. So for part 2 of the performance evaluation, we will look at the results for the external metrics. So even though cluster analysis is an unsupervised approach, we can create pseudo labels indicating how we expect the algorithms to cluster the stocks. The pseudo labels were generated from the industry/sector of the given stock. For external metrics, we primarily looked at entropy and purity. Purity is the percent of the total number of stocks that were correctly classified, while entropy is an information theory-based metric describing the probability of a stock being correctly classified given a cluster. Purity works as a percent ranging from 0 to 1, while entropy is a value that will range between some negative constant and 1. As we can see on the diagram on the left-hand side, soft DTW performed the best in terms of maximizing both entropy and purity, indicating that it correctly classified the stocks better than the other algorithms. However, all algorithms performed relatively poorly as the average purity is only at 19%. meaning that on average, the algorithms correctly classified a given stock 19% of the time. However, we must emphasize that the external metrics are not as influential as the pseudo classes generated are not hard limiting, as we expect stocks within the same sector, as we expect stocks from different sectors to trend together. Lastly, entropy and purity were derived from the cluster confusion matrix, where each column represents the pseudo label sector and each row represents the cluster, and each entry represents the number of times a given cluster correctly classifies a given sector for that column. In this way, each column represents the number of times each cluster correctly classifies a given sector. From this, we can calculate the correlation between sector columns. We can see this on the right-hand side. These correlations indicate that sectors which correlate together indicate that they are correctly classified on the same cluster, indicating an underlying cluster of sectors. So as we can see on the right-hand side for the algorithm tadpole, we can see the R-squared value for for healthcare and information technology is at 0.933, indicating that when tadpole correctly classified the healthcare sector, it also correctly classified the information technology sector. Now, this would be a very interesting further analysis where we can perform clustering on these underlying sectors. Now we will move on to the next slide for system architecture. So the GUI selected for this project is built off Flex Dashboard, which is an interactive dashboard for creating R Shiny applications. Shiny is a native R package designed for creating GUI applications built off JavaScript and CSS. The system architecture works by giving the user options on the dashboard for customizing output through the usage of interactive widgets, such as drop-down selectors and buttons. These front-end widgets work by connecting the R backend through a linkage port that calls the given corresponding functions. These backend functions then update the reactive variables that are then fed into the GUI plots. And now we're going to move on to the graphical user interface. So this slide gives the user gives you guys, the viewer, an overall glance. The user interface is set up to facilitate interactive analysis. The GUI is accompanied along with many different types of widgets for the given purpose of the user, and then outputs these functions consist of tables and plots. So for example, the tables are built to be dynamic to allow the user to search and range the stocks based off certain columns, while the plots are built to show the trends of the selected stock and the neighboring stocks within the given cluster. Now, even though this is a brief introduction to the GUI, we will cover this later on when we actually give a demo.
Great. Now I'm just going to finish up with the conclusions and kind of what we ultimately put together from this analysis. We ultimately found that the clustering algorithms are capable of identifying conjugate sets of stocks with both quantitative and qualitative analysis. As we saw on that last slide, I mean, this is a real example of clustering for ExxonMobil, and it correctly identified a set of 4 other stocks that trend very closely with it and could potentially be useful for predicting. The internal metrics, while they were somewhat different between, for example, the k-means algorithms and the distance peaks algorithms, they were similar enough that each of them is still useful. And like David was talking about, the k-means algorithms are more geared towards internal metrics inherently. So we still think that all of the algorithms we used were valuable. Unfortunately, as David also mentioned, the soft dynamic time warping is too slow for use in this case. This is something we potentially hope to correct in a future iteration of the tool as we look at 2 other use cases and possibilities for expansion. But the ultimate conclusion of this project is that we were able to put together this tool that is designed to facilitate an iterative process that will allow users to test and visualize different perspectives on stock analysis. They can come in and look at 3 different algorithms, change up the parameters as much as they want, whether it's their roll up or how many clusters they're actually looking for. The user can look at their target stock in different ways and come up to make their own analysis based on the results that the unsupervised algorithms were able to produce for them. From here, we have some future work that we would like to implement as we continue on in this project. First one would be to implement further algorithms in this tool. Obviously, we have 4 that we've implemented already, but there are other good algorithms that are constantly coming out every day. There's another dynamic time warping algorithm by Jean et al. That had similar results and similar use cases as soft dynamic time warping, for example. The next piece we'd like to implement is enable parallel processing. This would really help us in the fact that it would allow us to make some of the slower algorithms more valuable, like soft dynamic time warping. And we think that if we had more computation ability, we could also do more to actually tune the algorithm and make it function better. Finally, we'd like to implement some basic regression capabilities, whether that's with a Markov chain Monte Carlo methods or maybe a simple multilinear regression, so that the user can see some predictions for their stock based on the actual output. Thank you very much for sitting through the presentation. This next part, I think Brandon's going to take over the screen and we're going to have a quick demo of the tool.
Good. All right, so now we're at the demo for the GUI product. So at a first glance, we have the title, and then we have our team name, and then we have 2 tab sets. The first tab set is to just simply introduce the data, specifically the stocks, while the second tab set is to introduce the cluster analysis algorithms. So in the first tab, we have the following widgets on the left-hand side. Simply, we have stock symbol, as we can see here. So from the range of our given data set, we can select the different stocks. And then on the right-hand side, our interactive widget corresponds to our backend to update the graph. And then in addition to this, we also have the stock option. So from close, we can also look at open, or if we wanted to look something like at volume, the volume of units sold in a given date. And in addition to that, we can also change the date range. So let's say if we wanted to look at something from a year and a half ago, if we wanted to go to 2020, we can change the date range as well. In addition to this, we can also look at the roundups for the given stock. So we can go from day to week to year. And in addition to this, we also have a sub tab called roundups, where we have all the roundups for the given stock displayed. That way we can see the year, the month, the quarter, and the weeks. In addition to this, if this information given is not enough for you, you can also look at the stock table, which is simply derived from the roundup and the min dates. So right now we have it on year, which is why we only have 3 values. But if we were to change this, let's say back to weeks, we have the week roundup. So here we have the stock symbol, the date, the open, the high, the low, the close, blah, 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 yada, yada. In addition to that, we can also search the dates. So if we wanted to have a date range, or if we want to look at different open values or even search for different things, we have that capability. Now we're going to move on to the cluster analysis algorithms page. So first things first, before I explain anything, I'm going to run some parameters simply because this will take some time. So first off on the left-hand side, we have our widgets that we can use to customize the parameters for our cluster analysis algorithms. First, we're going to look at the bottom half. Simply, we can choose the min and max date range we want for our algorithm, and then we can choose the roundup and then the normalization method. In addition to this, we can also choose the cluster algorithms, which as of right now, we only have IK means, density peaks, and tadpole. And then we can choose the number of clusters. So after we run this, we click this button down here, and it's going to take some time for it to run. But once it finishes up, it'll display right here. All right, so now that the algorithm has finished, here we can see a plot of the final centroids. So here we have the closing value for the z-score normalization, and then we have the 4 centroid means. In addition to this, we also have a table for the internal metrics, where we have the cluster on the left-hand side for this column, and then we have the total sum of squares for the given cluster, and then the overall, and then the median total sum of squares per cluster. And in addition, we also have some other information such as silhouette score and min distance between centroids. But as we discussed in the presentation, these will be mainly for the soft dynamic time warping and the IK means, as they are based on Euclidean distance. And in addition, the next tabs that we're going to look at is the table of stocks within the same cluster. So simply what this means is we've put, oh, and before I discuss this, I'm going to discuss this, these widgets on the left-hand side again. So here we have the stock symbol. So if we wanted to select a stock that we wanted to visualize or examine, we would select this. But in addition to this, we have the option to import a stock from Yahoo. So this stock ticker BNED corresponds to Barnes & Noble's. So we actually imported this into our data set before running our algorithm. And then here we have the results. So right here we have the stocks that correspond to the same cluster as Barnes & Noble. And then here we have the sector for the given stocks, and then the norm distance between Barnes & Noble and the given sector, along with the correlation. So as we can see, this table is sorted based on the norm distance, meaning that these top 5 stocks are the closest to Barnes & Noble. So if we were to now look at the actual plots of these, we can definitely see that they all have the same similar underlying trend. So as we can see, we have the 5 top closest stocks in the thin color, while we have Barnes & Noble in the thick color, which is orange, as we can see here. So this gives the user the ability to distinguish between the given stock and the other underlying stocks. So in addition, once the algorithm has ran, we can change the stock symbol as much as we want. So for example, if we were to look at Tesla, we can update this, update ticker. Let me clear that out real quick. There it goes. So now we have the top 5 closest stocks to Tesla, as we can see here. And if we wanted to go back, we could look at the same cluster and then look at the sectors, the norm distance, and the correlation. So thank you for looking at this brief introduction and demo to the GUI program.